Okay, we're back again looking at the cell membrane. Again, the cell membrane, as we said, is a fluid mosaic, that everything's moving around and it's mosaic because it's made of several things. Phospholipid bilayer, we explained. Phospholipids, we explained in the previous video. Phospholipid, we talked about that several times. Integral proteins, peripheral proteins. Transmembrane proteins and peripheral proteins were discussed. Here would be an example of a remember, a protein is really a folded string. It's really a folded string. This looks solid because we're just making it look solid for those that can't abstract. You know what abstract is? Abstract is like some great artist comes, takes a coat hanger, and makes a giraffe out of it. Some people couldn't see the giraffe because they'd be looking through the spaces in the coat hanger. So he'd be upset and put some plaster Paris over it and say, hey, here's the giraffe, which would take the whole illusion away. Well, this right here is a solid picture, but really what a protein is, you recall, is a folded string. So this is just to show you that. Here's some function of the cell membrane. Transport, enzymatic, signal transduction, holding cells together, intracellular joining, attachment of the cytoskeleton. So as I alluded to, the cell membrane does a whole plethora of jobs. Transport, it moves things in and out. Some of the proteins wear two hats. They're not only a part of the membrane, but they're acting as enzymes. Signaling molecules, hormones, or other substances which sit on their receptor. Cell-to-cell recognition. One cell, this will be like an ANP2. This cell here is looking at this cell's flags to see. This will be white blood cells deciding, is this one of your cells or not? Holding cells together we'll talk about. An attachment of a structure we'll be talking about known as the cytoskeleton. Skeleton inside the cell, which is not obviously bone but made up of protein, but it does provide the shape. So you can kind of look at these. I put these in my PowerPoint. Okay. Now we're into cell membrane transport. Cell membrane I will have some videos, actual motion videos on cell membrane transport on some of them. But this is the introduction. Okay, this is kind of how I have it set up. I'm saying that you have something called passive transport. Passive transport means the particles that are moving in or out of the membrane. Let me say it again. The particles that are moving in or out of the membrane have their own energy. There needs to be no energy added to those particles. So the particles moving in and out have their own energy. Okay? Active transport. There are particles that want to move in and out, but they don't have their own energy. So they must acquire energy from that substance we talked about in chapter 2 called ATP. So passive transport, the particles have their own energy. Active transport, they need additional energy. Now, I put this in large particle transport. Okay, let me kind of explain what that is. So if we were in the classroom, let's say there was some large device in our classroom that was too large to be carried through any of the existing doors in the classroom, but we needed to get it out of the classroom. Okay? After the flood, there are several things that had to happen to. So, workers would have to come in and literally cut a hole. Would have to cut a hole in the wall to let those substances out. Would have to cut a hole. So my large particle transport means the cell membrane has to cave in. So with these two, there are doors it can go through. This one by its own energy. This one needs additional energy. This, you need to cave out the cell membrane itself. Okay? So what do we have listed under passive transport? Something called diffusion, something called osmosis, and something called facilitated transport. Facilitate, regular English, means to help. That means a help transport. But, check this out, it can't be helped by adding energy. It cannot be helped by adding energy, or it wouldn't be under passive transport. Active transport, primary active and secondary, we'll talk about. And then the phagocytosis, pinocytosis, and receptor under my large particle. Now this is kind of my own little designation here, right there. All right. Now the cell membrane has selective permeability. Okay. What does the cell membrane like to let through? Okay. Because the cell membrane, primarily, I'm going to go back to the cell membrane, is lipids, and lipids go through lipids. So something that is lipid soluble can go through the cell membrane in or out quickly, because it can go almost anywhere. It's like if somebody at the college, in the classroom, could go straight through the wall, they could be running much faster. We'd have to find a door. So lipid soluble things go in and out. If the molecular size is small, the smaller it is, the easier it is to go through. And uncharged, well, that kind of falls under lipid, because if something is charged, it likes water, and it won't go through lipid. So the three things that the cell membrane likes the best is something that's lipid soluble, uncharged, and small molecular size. Now, when you start relaxing that criteria, then things can go through, but they have to go through much slower. Things can go through, but they have to go through much slower. And there's finally going to come a point that the molecule is too big or water soluble or whatever, and it can't go at all. Does that say it absolutely cannot go? No, it doesn't. It said it may need extra energy, which would fall it under active transport. So just because it's not what the membrane wants doesn't mean it can't happen, but it means additional energy must be added, which would fall under active transport. So we go back here. All right. We already talked about this. Criteria for speed of transport you can read on. I kind of tried to lay everything out. Passive transport, no energy can be added. 3 types: diffusion, osmosis, and facilitated transport. Diffusion, osmosis, and facilitated transport. Okay? Let's talk on diffusion. Okay? Passive. Now I want you to listen to me well. It's the net movement of certain particles from a region of high concentration of those certain particles to a region of low concentration. Now my definition is a little more specific than what's in the textbook. Primarily on the certain particle aspect. Particles look at their own kind. Particles look at their own kind. See, in most textbooks you'll say net movement of particles from a region of high concentration to a region of low concentration. But actually that's not true, because you don't add up all the particles. You actually have to look at the individual kinds. Now let me explain net. Okay, what does net mean in math? Okay. Net in math means to subtract. See, when you say summate, remember on the computer, when you say in Excel, when you say summate, that means to add up. Net means to subtract. If you say, what's your net income? It would be your gross income minus your taxes. So whenever you say you're going to net something, that means you're going to subtract. Whenever you say you're going to net something. I said particles look at their own kind. Particles bounce around by entropic motion, Brownian motion. They just random. Remember, the universe likes entropy. They bounce into one another like people move into a crowd. So I made an example. Let's say this is a barrier right here. I have some A particles on this side, A's on this side, B, C's, and D's. Okay, this is compartment Z, this is compartment X. Okay, I have 14 particles on this side total and 11 on this side. So in a regular book definition, it would say, well, the particles primarily are going to move this way. Now, this is what I want you to understand. These particles are bouncing around. They're just hitting each other in a crowded room. You quite naturally, and when you hit one, you go back the opposite way. So if you're bouncing around and you get bounced into a less crowded room, you're not going to hit anything, and you'll probably stay over that way. So A particles, because there are more of them, they're going to get bounced more often this way. Not to say that some won't go this way. They don't have a brain. Vice versa, more B's would go this way, but some still would go that way. C's would go mainly this way, but some will go back that other way. So in other words, they bounce around for a long time until pretty much both sides have as many A's on this side as that B's, and that's what we call the state of equilibrium. So in other words, there's a net motion. Now listen to me. There's a net motion of the particles from one side to the other, from the high, but they're looking at each of their own kind. Interdiffusion. Interdiffusion. When the A's have evenly distributed, the A's have reached the state of equilibrium. The state of equilibrium. Now, technical point. Once they have reached the state of equilibrium, there's no longer any diffusion. Let's go back to the definition. Net movement of particles. If you have as many on one side as the other, you have no longer a net. It becomes zero. If you have no longer a net, you're not doing diffusion. So you reached equilibrium. You still are having motion back and forward, but you're not having any diffusion, because diffusion means a greater movement in one direction than the other. But all the particles look at their own kind. Here again, when the concentration on both is the same, that is equilibrium, but there's still motion. There's still motion, but it's as much motion one way as the other. So the net is gone. I want you to study that. Here again is looking at another one. He was looking at a beaker situation. So I've given you plenty of examples, plus some other videos that you'll get to kind of get an idea. All right. I'm going to end it here because our next subject will be osmosis. We will do that in the next video. All right. Thank you.